outside in the world, when there's a huge voltage difference between the sky and the ground, you get lightning. Because it actually breaks, that voltage difference is enough, the electricity wants to flow bad enough that it breaks the air into pieces, and that broken pieces of air results in charged particles, and that's able to carry the current down. That's what lightning is. So when you're working next to this tank, and the voltage gets too high, and it's not pure enough inside, you get lightning. This is the top here, this is the inside of the tank. Gives you a little bit of sense of scale. This is the central tube where it gets charged up. This tank is kept in the dark, and there are little windows. And what we put is Polaroid cameras. I don't know what they do now, but when I was there, we put Polaroid cameras on, looking through these windows. We seal them up so it's completely dark inside. And then as you're sitting there working, doing your experiment, you'll hear a thunder, basically, a big bang. And you say, and you watch the voltage on the machine go down, and your particles stop, and you say, okay, we know what happened. What happened was, it was some kind of lightning inside. This is an actual picture from when I was there. This is one of the bangs. We ran out, pulled the slide, and I have a Polaroid film here. It's exactly what this picture is. Scanned in there. So the reason we take these pictures is because, obviously we don't want this, it stops the experiment. But the reason we get the lightning, it's designed, and we want to go in high energy as we can. So it's designed to go to high energies, but we keep it kind of right on the edge of where it's about to break down and do this. When this happens, a lot of the time it's because there's a little piece of dust or something sitting on the inside of this tank. You see guys walking around it there, but it has to be polished very, very cleanly. And when we see the picture, say, okay, this lightning went over here, go in the tank and see what, somebody left a crumb in there or something. There's not a screw, but something could be in there. And that's why there's an easier path for it to go. And so we take these lightning pictures, but they make the pictures. So that's the lab. I want to show you I do have from the dedication, which was August 7th, 1987. Every time we dedicate a new lab, make a nice little book. And so I have up here, if you want to come look at the end, it's a bunch of pictures of what it was like, what it looked like to build it, and Vice President Bush coming for the dedication ceremony and all that. So that's a fun souvenir. So I have to be. So where am I? I have gotten to the point where, okay, so I got my nucleus from the Russians. I added energy to it in that accelerator. Now I've got to watch it decay, and I've got to measure. So how do I do that? When it decays, it gives off, as I said, this pattern. Now I need to measure this decay. I need something that detects photons. And what I use to detect the photons is some kind of a photon detector. There's all kinds of gamma detectors out there, photon detectors, all different kinds of energies, and different kinds of properties. The ones that we use are called germanium crystal photodetectors. I make a germanium crystal. Somebody else makes this. Commercial companies do this. And then when that photon comes in, it creates a little spike of electricity inside this crystal that grows as it moves toward the back of the crystal. And I'm able to then see that, first of all, a photon came in. I can measure what energy it came in at. What color it was, how much energy it had. And that's what I need to know. What I'm doing here really is in the experiment, to measure this thing, I'm counting how many I have. Most of the photons come off this way, not so many come off that way. I want to know what this pattern looks like. I want to know how it's oriented. So I'm really just counting photons. But I have to count the right ones. If I count the ones that are coming from space, or if I count ones from other reactions that are going on, or some other collision that happened that I didn't intend to happen, then I'm not going to get the right count. I need to count only the ones that I want. So I need to have a detector which can, first of all, measure the photons, see them come in, and see how much energy they have. And that's what these germanium detectors do. The challenge with them is they have to be kept very, 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 very cold in order to work. And the other challenge is they're made out of single germanium crystals that are hard to grow and very expensive and very fragile. So what they look like, what the experiment will look like, is this. This is from our beamline at Yale, at the accelerator with the big picture I just showed. What I have here, these steel cylinders, these cylinders here contain the crystal. So I have 4 of these detectors, and each one is connected to a big tank. This is just a tank of liquid nitrogen to keep it cold. So every few hours, the grad students have to take a big bucket of liquid nitrogen and go pour it in and put them still on their feet. Your feet get cold and your contacts really dry out from all this buildup. Nitrogen comes out. So this is where my experiment is happening. The beam comes from the accelerator, it's steered through here. This is a vacuum gate because we don't want that lightning to happen. And the guys that run the accelerator don't trust guys like me. So I had this thing that I put in. I've got to get the beam into it. But they don't trust that I did my right job here, keeping that sealed up. I might put something in that might leak back into the detector and cause the lightning. So they put a gate here that they control in their control room. And if they see something start to dribble down here, they've got detectors down here, they shut the gate on me immediately and my beam stops, but they protect their machine. So that's what this piece is. It's like the gate that controls the beam coming through. So the beam will come through here. And this is my experimental chamber where I put my target, my stuff I want to smash together. And that's surrounded by my 4 detectors. My 4 detectors are sitting here to look at this. And you see the way they're kind of in a pattern, but not an exact pattern because this is not an exact cloverleaf. But the other thing is what I'm really looking for is how this changes if this moves around a little bit. And if I'm sitting at the top, right here with my detector, and it moves back and forth, I don't really see that because I'm still right at the top. If I'm sitting here, I won't see much. I won't see much anyway. But if I put my detector right here, then if this moves a little bit, it's a much bigger difference in how many photons I get, how many gammas. So I set up my detectors in a pattern where I can see that. The stuff that's on the top and the bottom here, it's little coils of copper wire. That's to create a magnetic field. This thing, remember, this is the spinning magnetic field that I'm trying to measure. If I put a magnetic field around the outside of it, then the 2 magnetic fields interact, and I twist this pattern. Twist it this way, twist it that way. How much it twists is what I'm really measuring. That's what tells me the shape of the universe. How much this pattern twists in the magnetic field. Because that'll tell me the distribution of the charges within that nucleus. So I have this magnetic field which I can turn on and off and turn right side up and upside down. So run it for 10 minutes with the magnetic field in one direction, shift it this way, flip it upside down, see it shift the other way, and count those differences. That's how the experiment proceeds. This is the same type of experiment. I'm doing the same experiment here, but I'm at a different facility. This one was in Berkeley originally. I did half the work at Yale and half the work at Berkeley. It has since moved to Argonne National Lab in outside of Chicago. This is called Gammasphere. These are the same detectors. This is the same tank that holds nitrogen. The goal with this was to get all those crystals, all those remaining crystals, into a ball in one tight space. So I can see not just a simple pattern like this, but if I'm doing something more complicated, where these things go. There's no real way to do that to cover all the area, to go anywhere. So people spend a tremendous amount of the Department of Energy's money and a lot of time designing this really very nice detector to get this ball of all these things together and figure out how I can get all this liquid nitrogen cooled crystals all in one place at one time right at the beginning. You see now these things have big fat hoses coming off the back. That's because instead of having grad students come and fill these 100 things up on a ball, some of which are upside down, they needed an automated system to do it, which for the kind of physics I did, this nuclear structure physics, it's small scale stuff. Our teams are maybe 4 or 5 people, maybe 12 if it's a big experiment. It's not like the experiments we'll talk about in a couple of weeks, which are huge and have hundreds of physicists working on them. So you have to, it's all kind of homemade, taped together. We had a problem once where we needed cloth diapers in order to wrap around the cooling system, and they got rejected by the purchasing people all the time. They wouldn't refill it because we had people that they wouldn't refund the cost of the diapers because the people working with us had small children. So they didn't know what's going on. Pictures, come on. So there's a lot of, always running to Home Depot to buy big springs and else. This had to be done a little bit more professionally. Professionally enough that, first of all, middle school, this picture, which is not recent, was, this is the same chamber. It's a similar copy of the chamber. The beam now comes through here. I have the magnet on the top and bottom. This arm is to keep my target cold because for this particular work, it had to be cold. It turns out this is a very popular picture to take. Everybody posts themselves in front of us. What you're looking at here is this ball. It opens up. See, there's a crack here. It's on rails. The whole thing pulls apart. You get inside the thing, and then you close it around and do that. This was attractive enough that this is actually a scene from the Incredible Hulk movie. I didn't realize until recently because I left a while ago. And this is it. This good Hulk picks something up. This is how they made the Incredible Hulk. The movie is with this actual detector. This thing, it's called Gammasphere. I have the other book that I brought today to look at is the dedication ceremony for Gammasphere, which was 1993 is when it started. 93, 97 was the beginning. Again, this is at Argonne, but half of my work was done at Gammasphere, half my work was done at the other facility. The facility at Yale was the accelerator that I was showing you. We built the rest of it ourselves. This was at Berkeley. There was a called the 88-inch cyclotron, because it's 88 inches and because it's a cyclotron. We'll talk about that when we talk about accelerators later. It uses a different mechanism for getting the particles to go faster. But the key feature here was they had this detector that we could use, so we didn't have to build our own setup, and we could get stuff at a different energy. It's a nicer facility to work at.
Just to follow up on it, what does this experiment cost?
The detector array is built. I mean, it's a lot of millions. It's it's tens of millions, but it's not hundreds of millions. So it's not a huge investment. Most of the cost, a lot of the cost is just figuring out how to make the ball and make the thing. Labor is cheap, both for professors and grad students, much cheaper than hiring DoD contractors, which I know appreciate. But you build this thing, and then when you have the accelerator, you have the detector array, and then that's kind of open for use. And anyone can apply. It's kind of like writing a grant proposal. You write a proposal for the kind of work you want to do, the experiment, how many shifts you need. These things run 24 hours a day, and you say, it's 8-hour shifts. You need 18 shifts in order to do this measurement. They review it. If they approve you, they say, okay, you get 12 shifts. You figure out how to do 12 shifts.
It wasn't just your experiment.
No. This is shared by the entire community. So which is also, you get a lot of interaction too, because you're always going to these places and waiting for the last guy to finish so you can get started. And, there's a lot of collaborative work here between people that are not actually working together. So what I showed you was the accelerator and the setup that we did for detectors. What I'm showing here is really the detector. The accelerator is another part of the facility on the other side of the wall. So these detectors detect, what I get out of the detector is, again, I'm counting photons. That's all they're doing is counting photons with energy. So what I have here is the amount of energy that the photon had. This is counts, how many I have. This is 10, 100, 1,000, 10,000, which is why it looks kind of funny, it's not flat. And what I need to say is, okay, I was looking for my particular nucleus to decay. I shot a beam of something, I excited it, and I want to see it decay. What happened? I only need to look at the peak for a line. So maybe this is the energy of what I want, which I know ahead of time because I know enough nuclear physics to know what I'm looking for. But I have all these other things that are out there. So the first thing I do is I get this, I get home with it after running 24 hours a day for 10 days or something. First case facility, and then come back and start looking at the data. So I see all these peaks, I say, okay, I know what reaction I was doing, I know what I had in my target, I know it was in my beam, so I can identify all these peaks and kind of cross them off and ignore them. When I first started doing this, I kept getting this weird peak right here. Not a huge one, but it's simple. What is that? I'm not supposed to have it. That wasn't my beam, that wasn't anywhere. And one of the older guys comes over and says, it's potassium. It's potassium. It looks like potassium. Why do I have potassium? The walls. The walls are concrete in all these places. Concrete is made from limestone. A big component of limestone is potassium, and a lot of the potassium is radioactive. Very slightly radioactive. It has a gamma ray at right about 1500 keV. Sits right there. And you always get this potassium line. So if you turn everything off and everything is dark and nobody's doing anything, you flip on your detector and you measure, the big thing sticking up in the middle is the walls. You're actually just looking at the walls with your detector. So whenever you're standing next to a piece of concrete, you've got 1500 keV photons that are coming into you from the potassium in the walls. It turns out that it's a great way to figure out where you are, because you get lost in these things sometimes. Your energy scale might be wrong. You don't have it calibrated. That's the first thing you have to do is figure out what the scale is. Where am I? You look for the potassium and say, okay, now I know where I am. Or I'm powered up or anything else. We also calibrate them by having radioactive sources. You get a little piece of something, just buy out of a catalog, and then stick it in front of the detector. You know exactly what it is, and you're able to measure what the energy is and calibrate the detector as you assign the scale. So I get these peaks, and what I do essentially is I go through and erase them all, except the one that I'm interested in. And now I have the background, and I have, let's say, this one that I'm interested in. And now I have to come up with some kind of a way to cross off all this stuff, because this is just background from anywhere. It's not very many counts. It's maybe, this is 10 photons that came from somewhere. And I don't know where, and I don't really care where. All I know is that there's some kind of background. But you see, it's not a straight line, it's fairly smooth. And it's fairly straight over certain regions. So if I'm here, I kind of do an average there and cancel all this out. And I just count the number of counts that are in this peak or in this peak. And that tells me how many I got. And that's a lot of where the work is. So it's, do the experiment for a couple of weeks, and then spend a couple of months going through each of these for each of the detectors for each run and going through that process. Sometimes you go through it, and after 2 weeks you say, I'm tired of this, I'm getting cross-eyed, And you decide to spend 3 months writing a program to do it instead of spending 3 weeks to actually just finish the work. And that's why grad school takes 6 years. So let's see, we're not quite there yet. So, yeah.
Why you get some plateaus in the decays instead of a straight down line?
Coming through here,
Uh-huh.
there's a lot of different background sources, and they're not all even. So it's not like I have background coming from one particular thing. I'll have cosmic rays that come from different processes that will have a certain shape. And those shapes are not, so this is a single nucleus decaying in a predicted way between 2 states that I know about. So that's why I have sharp lines here. For a lot of this other stuff, it's not a simple decay. It's a more complicated process. It's maybe a thermal process that has a bigger distribution. So instead of being a peak, it will just spoil like a hump like this. And it's possible in some cases to model those things. When I get to particle physics, I need to know each and every single individual thing that happened. I can't use this kind of an averaging thing. I can't say, well, I'm going to ignore the first 100 and I can't about that. In particle physics, I need to know exactly what happened with each interaction. And that becomes a much more laborious process, which is why particle physics takes longer than PhD. But in this case, it's all those different sources that just add up to a rough background that can subtract the background and put it all together. So I have this picture here. Now, the last piece I want to talk about is how I got what the experiment actually is, what's inside my target, what I'm really doing. So I have my nuclei that come in from my accelerator. So here's my accelerator. Nuclei come in, I make a target. My target has 3 layers. This here is what I'm trying to measure. So let's say it's pick neodymium. Not quite randomly, it's what I studied. But, I'll have something light that comes in here. I don't know, iron, doesn't really matter what it is, something light. So I have a light ball come in here, bounces off this ball and bounces back. So here's my nucleus here. The particle from the accelerator hits, bounces off, and creates my excitation. Puts me up into this higher state. So now I'm excited. I'm in some higher shell. I have some deformed shape. But I also have the energy that I got from being hit by this thing. So I've got 2 kinds of energy. Some of the energy went into moving me up to a higher state. Some of the energy actually kicks me out. So this layer was neodymium, because that's what I want to measure. And then that thing gets kicked out and flies through here. This layer is something magnetic. We used gadolinium, which is why it had to be kept cold. You could use iron if you wanted to here. And I get this big magnetic field. So now I'm taking this pattern, which I had in the first place, this clover leaf pattern, which was just kind of going to sit there, not going to tell me much. And now I put it through a magnetic field, and that's what makes this thing twist. And that's why I had the coils on the top and bottom of the experiment. And I can twist it one way, I can twist it the other way by changing what this magnetic field is. And I need to know how long I'm in that magnetic field, because the magnetic field makes a twist, say 2 degrees per second, something like that. So if I'm twisting, I need to know how many seconds that's happening so I know where I ended up. That's how I'm measuring what the magnetic properties of this nucleus is. Remember, what I'm trying to figure out is what shape this thing is. So I come through here, depending on the shape and the strength of the field in here, and on how long I'm in there, I'm going to change, it's going to determine how much I rotate. And how much I rotate is what tells me the shape. So I need to know, let's say this is iron, this is my magnet, how long I'm in here. So I hit this thing, it flies through, that means I need to know this thickness very well. And then I need to see it decay. So I have to have it stop and sit and wait until it falls back down from here to here, and actually gives me all my photons. So this, we use gold, because gold doesn't do much of anything, it just kind of sits there. And it actually, we use gold that's really thick. So it stops, somewhere in the gold. And it waits and it decays, and I measure that decay. So my job, the first thing I do is I gotta make this target. So I start with iron, I roll it out, or gadolinium, I roll it out until I get it to a certain thickness, that's the thickness I want. I then have to get that little vial of the tiny amount of stuff I want to measure, whatever my experimental thing is, and I have to make the front layer on that. And then I have to glue a bunch of gold to the back, or squeeze it to the back because I can't glue it because then I have a layer of glue in there, that would be a problem. So this is what I do. I also need a detector out here to detect this thing that came through and bounced, because I can't just leave this thing running all the time. It's going to be mostly noise, mostly cosmic rays. This background, all this other stuff is going to be all the way up here. My peak is going to be buried in all the other stuff that's going on around all the time. So I need a way to trigger, just take a snapshot. It's like a flash on your camera. I only want to take this picture when I think something happened. So to do that, I watch for the particle to come from the accelerator. It bounces off the nucleus I want, it bounces back. So this one goes forward, the one I want to measure goes forward, but the one that excited it bounces backward. I detect that, that's when I take my picture. That's when I take my snapshot here. That's the snapshot of this thing decaying. Now this doesn't happen at exactly the same time. I have to put a little bit of a delay in. There's a big rack of electronics and coils of wire in order to, because this will happen first and then I have to wait for this to happen. So I have to account for that difference. So there's a lot of setup that's involved there. But essentially that's what's happening. I trigger, that's the word trigger, the detector based on detecting the reflected particle. The particle that caused this process in the first place, that caused the excitation. And then when it stops, it decays, I measure it. So this is the basic nuclear structure experiment. It's called a transient field because there was a magnetic field in here that was enormous. This is actually, by doing it on a small scale with this technique, there's a little bit of magic that goes in here with the spins of the electrons. It gives you a magnetic field that's much, much, much stronger than anything you can make in a normal size thing. It's a bit of a magic process that happens. And that's the standard nuclear structure. Now, yeah.
Why do you need the magnetic field there again?
Because I need to twist this thing. I need to, what I'm trying to measure, this is the pattern that it will always have. Anything will always have this pattern that's going between these kinds of states. But what I really want to do is twist it and see how strong that field is, what that interaction is. And by twisting it is how I measure what the shape is. The magnetic field is what causes the twist. So I do this, and then with a certain kind of neodymium here, and then I do it with a different one. It's maybe this is 142, and then I take a neodymium that has 2 more neutrons, maybe 144, 146, 148. I do it again and again with different flavors of neodymium, different numbers of neutrons. And when I do it with different numbers of neutrons, I'll get a different shape. And I can measure how the shape changes as I add neutrons. So we talked about before, like, are we really adding neutrons? In this case, I'm just getting stuff that has different numbers of neutrons. There's other processes where I can actually add neutrons as I go. And see how, now I add 2 neutrons, I get one shape, I add 2 more neutrons, I get a different shape. And I'm measuring whether it's collected, whether it's single particle, whether it's squeezed, collate, oblate, all that stuff is just from that. The key thing that I did, this was the physics that I did. But in terms of experimental procedure, there was something more significant actually to my work, which was that here, I need to have the target of what I'm doing. The target has to be made out of the neodymium I'm looking at. And we have the problem of how much do you need? Well, you need some, you need enough stuff. I need a lot more stuff to make a physical target out of, and the target's probably about this big and very thin, but it's a macroscopic size. Much more stuff here than I need stuff to make a beam out of. So wouldn't it be cool if I could measure the beam instead of measuring what's in the target? The reason that is consequential is not just because it's hard to get a bunch of stuff, but because that would then allow me to measure radioactive beams. And we talked about before, we don't really know a lot of what the nuclear structure is when we get far away from that number of protons and neutrons that keeps it stable. When it's unstable, especially if I have too many neutrons, we know very little about what's there. And the reason we know very little about what's there is how do I study something that's unstable? I can't get a bunch of it because it's going to fall apart. If I have something that lasts for 1/10 of a second, I can't really study it. It falls apart first. So what my work was to be able to turn this picture around a little bit. And instead of using a light thing that would bounce back to measure a heavy thing, I would put the light thing in here, something light, and something heavy in here. So this is now heavy. This is called inverse kinematics. The heavy thing is what I'm accelerating. This is what I want to measure. And now, both particles, the big one and the little one goes through, and now my detector is over here, my trigger detector. And the big one basically follows the same picture and stops. It's a lot harder to do. One of the problems is that now my layer of gold in the back, instead of being this big just to stop it, has to stop the big thing but let the little thing go through, otherwise it won't go through and hit the detector and trigger this. I won't take my snapshot. The shutter on the camera won't go if the thing doesn't get through. But if this is too thin, then my big heavy thing comes through and hits my detector and I get the wrong result also. The other problem is that now, the reason for doing this is I can measure radioactive beams. I have something that I make and it lasts for 1/10 of a second. If it lasts for 1/10 of a second, well, it takes me less than 1/10 of a second to get this thing down the beamline, have this happen and decay. So I can measure something now that is radioactive. I can do measurements on something that only exists for a tiny amount of time. Whereas with any other technique, I can't sit there and look at it because it falls apart before I'm able to do the measure. So being able to measure the beam, measure radioactive beams, this work was the first set of measurements on the beam that you could do before radioactive beams, because we knew radioactive beams were coming. Now it's, I want to figure out how to do this later, but now radioactive beams are a standard thing that the accelerators are able to do. But at the time, it was right around the time that I finished my work, that the first radioactive beam had just got its first set of results there. There are a few other techniques that people use where they put a piece of film, like 16mm film, and let it run, because once you have the radioactive stuff here, it'll keep decaying. You need to get it out of the way, so there's a kind of a camera film loop running in the background here just to clear that stuff away. But this was the significance of the work that I did mostly. Okay, that brings us to next week. Okay, let's see. Okay, that's what we'll do next time. So that covers nuclear structure physics. That's the physics of the nucleus. What we're going to talk about next time is now, I had my nucleus, which was the big thing with neutrons and protons. Now we're going to take one of these things, a neutron or a proton, and look at what is inside of it. And what we'll see, there's a couple things we're going to need to do when we see that. I'll just leave you with this. Okay. When we see what's in a proton, there are quarks that make up the proton. There's the electrons and photons we've been talking about. And once I have these pieces, once I have the quarks, they're in my proton, maybe I can take those and rearrange them in different ways. It turns out I can make different particles. I'm not just stuck with protons, neutrons, and electrons. This is why it seems so simple in 47, when we thought we had the whole thing for about 6 months, everything was worked out. I can rearrange the stuff that's in there. And it turns out if I keep doing more work and I build bigger accelerators, and I start now smashing these things into pieces, new particles come out. Strange particles come out, including particles that are called strange. Just the strangeness of what happened didn't fit the picture. So we'll see there was a complete mess of what started being discovered as all these things started breaking apart. Nobody could figure out what was inside the neutron or proton to begin with. And you thought you figured it out, but then there's other stuff that's there. So there's a whole bunch of new particles you have. And then when you start looking inside the proton, it doesn't actually look like you think it looks. It looks like I had these 3 quarks in there, but it turns out when I measure them, if I add up the masses of the 3 quarks, I come up with like 1% or less of the mass of the protons. There's mass coming from somewhere that's not the quarks that the thing is made out of. If I add up the spins of these things, it adds up to about 25% of, once I measure them, of the mass of the spin of the entire proton. It doesn't add up that way. When I smash them, I don't get the right number of things coming off in the right places that I would expect to. So this is the story of what's inside the nucleon physics, which is part of nuclear physics. It's either the nucleus or the stuff that makes up the nucleus. And that brings us into particle physics, which is where we get exotic, where I start making all kinds of crazy things. And the standard model, which is pretty much a miraculous framework where it all comes together and it all makes sense. There's regular patterns for everything. I can predict all kinds of stuff, and everything really works beautifully up to certain shaggy edges that are actually being worked on. And there's certain things that you just can't necessarily explain all where that comes from, where the standard model comes from. And that's the kind of groundbreaking stuff that goes on now. But the picture that we'll see next week is really what the real fundamental parts are. Everything has been drilling down. We had the atom, we break it apart into electrons and neutrons and protons. I can break the protons, neutrons up, and we get to a point where we're going to identify the 12 plus 6 plus 6 plus 4 more, and maybe a few more, fundamental particles that are really the fundamental particles that everything's made up out of, where they come from, why they're there, and how you can play with them and make interesting things. So that's next week. We'll see you back then.